Hello gentlemen, welcome to our video on Chapter 21, Nuclear Chemistry. Now thus far in our chem class we've talked about one type of chemical reactions, or one type of reaction in chemistry, and those are chemical reactions. In chemical reactions, we have a transfer of electrons from one substance to another substance to give us a certain product. In nuclear chemistry, we have nuclear reactions, and that involves things happening within the nucleus of the atom where we have protons and neutrons. So let's take a closer look at the nucleus and revisit what that is. Now, the nucleus has protons and neutrons in them, and those two substances as a whole are called nucleons. Now, protons represent the atomic number, and your protons and neutrons together represent the mass number. So if we look at the isotopic notation here, my mass number is on top. In this example, we have carbon, atomic mass number of 12, and my atomic number here is 6, down here representing the number of protons. And sometimes down here in the bottom left, you have the number of electrons represented there too, and we'll talk about that in just a moment. Now, not all atoms of the same element have the same mass, and that's due to having a different number of neutrons, and we call those atoms isotopes. Down here we have examples: uranium-234, uranium-235, and uranium-238. This 234, 235, 238 represent the mass number of the atom. They all have the same number of protons because they're all uranium. However, the number of neutrons differ, as we can see. Uranium-234 has 142, and so forth. We call these nuclides. Now, nuclides is a fancy way of saying nuclei, which is the plural of nucleus, nuclei that have their own specific amounts of protons and neutrons. So, own specific amounts of protons and neutrons, they're called nuclides. Now, our major concern for this particular section is going to be our proton to neutron ratio, because any element that has more than one proton, basically anything but hydrogen, will have repulsions between the protons in the nucleus. Because neutrons aren't charged, in the nucleus we have a bunch of things that aren't charged with a bunch of protons that have the same charge. So protons, all being positive, are going to want to repel one another. But they don't completely, meaning the nucleus doesn't just fly apart because of the repulsion forces. There must be something else there that is holding the protons and neutrons together, and that is something called the strong nuclear force. It is the strongest force known to man as of now. It holds all matter together. So that strong nuclear force holds neutrons together with neutrons, holds neutrons together with protons, and it holds protons together with other protons. Now, this strong nuclear force is only dominant when your neutron to proton ratios are what we call stable. When they're close to 1 to 1, they're pretty stable. But as you get closer or further away, when you have maybe too many protons to neutrons or too many neutrons to protons, it becomes an unstable nucleus. And an unstable nucleus is going to want to reach stability. But first, we call an unstable nucleus a radioactive nucleus. So when we talk about radiation or radioactive isotopes, we're talking about an isotope that has an unstable nucleus. And this overall discussion is called radioactivity. These radioactive nuclei can also be called radionuclides. Now, there are several ways radionuclides can decay into different nuclides, meaning they decay to reach stability, as I just said. Now, let's talk about this decay. It's called a nuclear reaction. So that's one type of nuclear reaction. We'll talk about the two types here: fusion and fission. Fusion is combining the nuclei of two or more isotopes to form different nuclei. So you're just combining the nucleus of one atom and the nucleus of another atom to make a different nucleus. Pretty simple concept. But when you do this, you release a ton of energy. This is how the sun creates its energy. Man has tried to duplicate this, but has not been very successful in doing so. But fission, however, is our ballpark here on Earth. This is when we have a heavy nucleus and it splits spontaneously or on impact with another particle. And I have a picture down here representing how we do this on Earth. We take some kind of particle, we fire it at a different particle, a nucleus here that is particularly unstable, and when we do so, that nucleus splits. So we call this splitting atoms. And I'm pretty sure you've heard of that. So we split these atoms and they turn into different nuclei and some particles left over as well. Also, a ton of energy is released. Not quite as much as fusion, but still a great deal of energy. Now, this process of fission oftentimes is accompanied by decay. Not oftentimes, every time pretty much. So this nucleus, to gain stability, is going to decay into different substances. There are 5 types of decay that we'll talk about in this video. Our first type is alpha decay. Now, alpha decay is the loss of an alpha particle. Alpha particle is a fancy way of saying just the nucleus of a helium atom, which is this here. Helium has mass number of 4 and atomic number of 2. So 2 protons, 2 neutrons, making a total mass of 4. Let's say we have uranium-238. It's an unstable nuclei, so it's going to want to decay and reach a more stable position, meaning my proton to neutron ratio wants to get to a more stable ratio. When it does, it's going to lose an alpha particle, and when it does, it loses 2 protons, so it goes from 92 to 90, and the element that has 90 protons is thorium. And because it lost a mass of 4, it goes from 238 to 234. So this is thorium-234. This is a nuclear equation. It has to have balance, just like a chemical equation. We have to have our mass and charge both be balanced, and the balancing is going to be determined based on what you lose, what is being decayed, essentially, what is coming out of the nucleus. This is alpha decay. Decay is beta decay. Beta decay is the loss of a beta particle. A beta particle is a high energy electron and a high speed electron because it has so much energy. The symbol for a beta particle is this or this. Conventionally, if you're talking about a beta particle, oftentimes you may see this more often because this is going to represent something else later on and it can be a little confusing. Now, our nuclear reaction is, say we have iodide 131. If it loses a beta particle, we go to xenon 131, and here's our beta particle. Here in this case, I use this notation. But this is pretty weird because we know that electrons are just a negative charged particle. So what's weird about this is that if we lost only an electron, how could my atomic number change? Because atomic number only changes when you have your protons altered. So here's the scenario. The nucleus has too many neutrons and not enough protons to balance those neutrons. So it's considered to be unstable. So what's going to happen is a neutron will turn into a proton. Now neutrons and protons aren't very different in their makeup. We'll talk about quarks in class, and the quark makeup and configuration isn't that different between a neutron and a proton. So they can kind of transition into one another, neutron to proton or proton to neutron. I wouldn't say easily, but it's not impossible. So a neutron will turn into a proton. And in this process, a new high-speed electron called a beta particle is made, and it shoots out of the nucleus. So that's why we have a change from 53 to 54, because a neutron turns into a proton. So we gain a proton, which makes my atomic number go from 53 to 54. And when that happens, so does my element changes, because the atomic number serves as the identity of the element. This is beta decay. Is positron emission. This is something a little new. We haven't talked about positrons before. So some nuclei decay by emitting a positron. A positron is a particle that has the same mass as, but the opposite charge to that of an electron. So it's a positively charged electron, essentially. But we don't call it an electron, we call it a positron. Now, what happens in this scenario is the nucleus has too many protons and not enough neutrons. So a proton turns into a neutron. In this process, a positron is created. So a positron is the opposite of an electron. Again, it's kind of the opposite, well, I wouldn't say the opposite of beta decay, but the nucleus has too many protons, so a proton turns into a neutron. In this case, you had 6 protons in the case of carbon, and you lose one, and it goes to 5. And when that happens, you become boron. So you change your element, and now this is way more stable than this was, so everything's all good. And notice we still have a mass to charge balance. My mass hasn't changed, 11 to 11, 6 to 5, and my 1 here balances out my charge. I have positive 1, positive 5, matches my positive 6 on this side. This is positron emission. My next type of decay is gamma emission or gamma decay. Now, gamma emission is a loss of a gamma ray. This is the symbol for gamma, which is high energy radiation. It's not a particle. It's just high energy. And it's always accompanies the loss of a nuclear particle. Meaning, so those other types of decay that we just talked about, when those go on, oftentimes you'll have gamma emission happening simultaneously with it. So oftentimes when those other particles are emitted, you'll have gamma decay happening as well. And because it's just energy, it has no mass, it has no charge, it's just high energy. So typically this is not shown in the nuclear equation, as you just saw in our last examples. I didn't have this written there with it because it's usually not shown, but this is gamma emission. If you're a fan of superhero, comics and stories, this is usually what gives them their superpowers, gamma radiation. Our next type of nuclear decay and final type that we'll talk about today is electron capture, sometimes called K capture. This is the addition of an electron to a proton in the nucleus, and it's known as electron capture again. The result of this process is that a proton is transformed into a neutron. Now, this is a little bit different. In this particular example, the particles are going into the nucleus instead of out of the nucleus. So not necessarily considered decay. This is kind of, we can say decay with these quotes here, because it's not really decay. Things are actually coming into the nucleus. So as you can see, our equations kind of change. We have two things becoming one thing. Not necessarily considered fusion either, because this isn't really a nuclei. Okay, so what happens is, in order to achieve stability, we have an electron going, and this electron here comes from the electron cloud. So from the electron cloud, the electron goes into the nucleus. And when it comes into contact with the proton, that proton with the electron turns into a neutron. That's electron capture. This is pretty similar to beta decay in that it's kind of just the opposite of it. So gentlemen, please take notes on this. We'll go through these again and add a little bit more detail to some of these scenarios. But this is nuclear chemistry and radioactive decay.